No, not that one. This one. Hello, everyone. Welcome back to another wonderful afternoon of Pre-Calc 1. Just as a reminder, your usual due dates are on the screen. The review is still available. The test is still available. That'll close out 11:59 p.m. tomorrow. That is Friday the 17th. Please do not miss that opportunity to take the test. Remember, you get two attempts on this. I only count the highest one. If you do not take it, there will be 0 makeup opportunities unless you have been just ill for the past 2 weeks or something like that crazy. Chapter 2 homework is due tonight. Again, no exceptions to that. Besides that, we need to pick up where we left off in 3.2. So 3.2 continued, polynomials and their graphs. So in 3.1, we graphed quadratics. We learned a new, better way of graphing them using multiple points. 3.2, we're learning how to finally graph polynomials. We never really focused on graphing polynomials in the past. Sorry, I'm getting my headset straight. So we had a few things to build up to, or a few things to develop in order to build up to graphing. And the first thing was the leading coefficient test, which we related to the graphs of x squared and x cubed. The next thing was the multiplicity of zeros, which we also related to the graphs of x squared and x cubed. So those are really, really potent graphs. And we left off here. We want to talk about turning points. Now, this is not something that I always ask people to describe in a problem, but it's a good thing to have because it's another one of those self-checks. Kind of like when we were graphing the quadratics, we said that you should look at the leading coefficient to tell whether it points up or down, but honestly, that just happens if you do everything else right. Same thing here. If you do everything right, the number of turning points should be seen appropriately, but the graphing process is a little, pun intended, sketchier, it feels like, with this more complicated process. So it's something that I think is a little more important to have in your mind while you're doing this. So what exactly is a turning point? Well, a turning point is a max or a min, and I'm not going to be able to do this too far on the side, but my pen right. And let me switch colors. So let's say this was our graph, this red thing over here. The turning points are your local extrema. So those 3 dots, the maxes, the local maxes and the local mins, those would be our turning points. I'm not using TP as test point here. Please listen to the words coming out of my mouth. Those are turning points. So there's 3 of them for this particular graph. Now, what we make note of here is that if a polynomial has a degree of n, then it can have at most n minus 1 turning points. So in other words, if your polynomial is a 5th degree polynomial, if the largest exponent's a 5, there can only be 4 turning points. There can be 1 less than the degree in terms of turning points. So if the degree is 7, there can be 6 turning points. If the degree is 2, there can only be 1 turning point. This holds true for all polynomials. Now, it does not guarantee that many turning points. A polynomial that's a 7th degree may have no turning points, in fact. It is entirely possible. It could have no turning points. It could have 1, it could have 2, it could have 3, it could have 4, it could have 5, it could have 6, but it couldn't have 7. Now, admittedly, some of those options I just mentioned are not feasible for other reasons, but we can just say for now it's between 0 and 6. So this is going to be an excellent concept to use when we're graphing. But let's say we had to graph something that was like x to the 3rd plus da 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 da, and we said this was our graph. Well, guess what? That's not even possible because there's 3 turning points, and the polynomial is 3rd degree. The most number of turning points it could have is 2. So that wouldn't even be possible if our polynomial's largest term was an x cubed plus et cetera, et cetera, et cetera. So turning points, definitely helpful for graphing. Something else that's helpful for graphing, using symmetry. So if you think there's some symmetry, you could plug in -x and see if it spits out the same as the original function. That would make it even. Or if you put in -x and it spits out the same as the opposite of the original function, that would make it odd. This is, again, not a mandatory thing to do, but you will hear me speak of symmetry every now and then because the problem has symmetry and it would be helpful. But again, not that often. But what you really, really, really have to have down is finding the zeros by setting the function equal to 0. That has to be mastered. If you can't factor, you are out of luck. You are not going to be able to do this without the ability of factoring. Identifying the multiplicities of zeros, telling whether they bounce or cross on the axis, that is important. Using your leading coefficient test to know whether the ends are going up, down, or one of each. Those are all very important aspects. So we're going to put this all together in one big recipe to graph any polynomial. Now this 5-step process, what do I want to say? Step 2 can be much, much more complicated than just factoring. And we will see that start to develop in 3.3. But for now, it'll be factorable, or it's already factored to begin with. So first, use the leading coefficient test to determine the end behavior. So that's where we are saying, oh, okay, we have, for now, no idea what happens for the bulk of the graph, but we know maybe the left goes down and the right goes up based on the above rules. And there are 4 possible scenarios for that. So that's your leading coefficient test. That's the first thing you should do so you know what happens at the ends. Then you find your X and your Y-intercepts. This was the name of the game in the last section when we were graphing quadratics. You're still finding intercepts in this section. When we go to graph rationals, we're still going to find the intercepts. And for exponentials, you can still at least find one of the intercepts always. The other one's not always findable, but we'll get into that later. Maybe. So find your intercepts first. Do the X-intercepts by setting the whole thing equal to 0. Then do the Y-intercepts by plugging in X equals 0. Do you have to do these 3 things in that order? Nope. You can find the Y-intercepts, then you can do the leading coefficient test, then you can do the X-intercepts. The order of the first 3 steps doesn't matter. But once you start connecting the dots and everything, and you'll see these little hills and valleys develop, you want to then make sure that you don't have too many turning points. So again, if your degree is a 4, but you have 17 turning points, if you just make some graph that looks like this for whatever reason, that's too many turning points probably. And then use symmetry if possible. You could do symmetry before the turning point. You could do it after. There's a little bit of pliability there. And again, honestly, I'm not even going to be using symmetry in this section, but we'll see it pop up later. So this is our 5-step process. Arguably 4 if you don't bother checking symmetry, because all of these can be done without symmetry. Maybe you need an additional point or 2. That's not really going to be an issue now, but it will be later. Again, we kind of make things worse as we move along. And by worse, I mean more complicated. So leading coefficient test, intercepts, check your turning points. And then it's just connecting. You're always going to make some type of shape that's bending like this. Maybe there's not that many hills. Maybe it's only 2 hills. Maybe there's 7 hills. But it should be bending and making these little hills and valleys. That's what all polynomial functions end up looking like. So if you draw something that's doing this, I mean, that's clearly not even a function. That would be a bad idea. So they'll look like these, and you're only going to get a couple of points and end behavior, and then you have to connect those dots to make that happen. Now, I didn't say this out loud, but it is here. When you're finding your X-intercepts, make sure you identify your multiplicities. That's going to be critical because knowing whether we bounce or cross on the axes really helps us develop those hills and valleys appropriately so that there aren't too many or too few. Well, all right, enough talk. Let's have at it. New share, whiteboard, maximize. Example, what are we up to, 3? No, 4. And we're going to graph the polynomial. For a, we got f of x is equal to x to the fourth minus 2x squared plus 1. All right. Oops, sorry, I was organizing. So the first thing we want to do is find the end behavior, EB end behavior. So that's where we just look at the leading term, the thing with the biggest exponent. It's not always the first one. We did an example where it was not the first one last time, but it is the first one here. So that's an x to the fourth. It's an even exponent. The leading coefficient is positive. So what that means is, I want to erase that. I don't want that there forever. So what that means is our end behavior, we have no idea what happens in the middle, but both ends will go up. Even means they go in the same direction. It's a positive leading coefficient, which means they go up. If that had been a negative, they'd both point down. There we go. So there's our end behavior. For the next part, we'll do the intercepts. And I said X-intercepts first. It doesn't matter, but that's where we set the function equal to 0. So we go x to the fourth minus 2x squared plus 1 is equal to 0. And this is factorable. As I promised, all the problems in this section are factorable if they're written in a standard form. You could use a substitution. Some of you might want to say let u equal x squared, and then u squared would be x to the fourth, and that's factoring u squared minus 2u plus 1, and then you go factors of u. Honestly, you start seeing this kind of pattern so many times that I feel like most students end up just realizing that instead of being an x in the first spot of the parentheses, it ends up being an x squared. And if you don't see that, you can again use a substitution. So maybe you want to say let u equal x squared so that u squared is x to the fourth, and that gives us u squared minus 2u plus 1, which then factors as u number, u number. Well, the factors of 1 that add to 2, well, the only pair that exists is 1 and 1. And to make sure they add to 2, they'll need to be the same sign. They're supposed to add to a negative 2, though. So those are minus 1s. So as u's, it'd be u minus 1 times u minus 1. But here it's x squared minus 1 times x squared minus 1. And again, you can get all that by doing the substitution, but a lot of people think it's optional now. It's up to you, pun intended. Now, what some people will do here is they'll say, oh, well, that's the same thing, so let me just write it as x squared minus 1 squared. That is true. However, a lot of people will end up making mistakes if they go that route. So let's only combine things if they're linear factors. This x squared makes this a nonlinear factor, so I'm not as inclined to squish these together as one parentheses and squaring it. Again, it's technically right, but people tend to make mistakes when they do it that way. Let's factor each of these, and of course it's still equal to 0. X squared minus 1, each of those is factorable. That's x plus 1 times x minus 1. That's the difference of squares. Again, this pair of parentheses was x squared minus 1, difference of squared formula. But it's the same thing after it, so we write the same thing after it. So we get x plus 1 times x minus 1 times x plus 1 times x minus 1, 0. Now let's combine factors. Now that nothing else is factorable, let's squish together the common ones. There's an x plus 1 and an x plus 1. That's the first and the third. So that's x plus 1 squared. Then there's 2 of those x minus 1s. So that's x minus 1 squared. All right. Now, once these are factored, if there's exponents, we said the exponents don't really matter when we do our zero product rule. We just set the insides equal to 0. The exponents are the multiplicities. So we're going to go x plus 1 equals 0, or x minus 1 equals 0. So I'm going to skip showing the work because I'm running low on space. Subtract 1 on both sides, add 1 on both sides. You get x equals negative 1 and x equals positive 1. but we still want to identify their multiplicities. That's the exponents. Both of those have exponents of 2, which means they bounce. Remember, odd multiplicities cross, even multiplicities bounce. Now those 2 points, and I'll put it in a different color for emphasis. So our X-intercepts are -1, 0 and 1, 0, and both bounce. Both bounce. And then move some things out of the way. All right, step 3. This is the Y-intercept, which is where we're doing f of 0. Well, that's 0 to the 4th minus 2 times 0 squared plus 1. All the zeros go away. We just get f of 0 equals 1. So as a point, that's 0, 1. There's no bouncing, there's no crossing on a Y-intercept. That only relates to the X-intercept. All Y-intercepts have to cross. They have to go through. It has nothing to do with the multiplicity. Step 4, turning points, the maximum. Well, the degree is 4, which means it can only have 3 turning points. There can only be 3 peaks or valleys. So let's put all this together. And in a slightly different color, I'm going to represent the end behavior. Let me do that in green. Yeah, green. The end behavior. It said both ends go up. Actually, since it's red, I'll do red. That makes sense. So since I say the ends both go up, just on the far left side, I'm going to draw arrows pointing up. Now, one of these we're actually going to use to start the problem. We're going to start from the left, and we're just going to make that polynomial shape something like this. I'm not saying this is what it looks like, but I know that on the right side, it's going to have to go up so that I match the end behavior. So I'm going to undo all of that. So I know if my graph looks like this, that's wrong, because on the left side, I'm going down, but it says it's supposed to go up. So I know where to approach from. Or maybe I start from the top, so this is good, and I make some waves, and I end up looking like this. Well, I know this is wrong because my graph says it points down, but it's supposed to point up, so that does not agree. All right, so we're going to start from the top left. I'll do the graph in blue. So we're starting from somewhere up here, and we got some intercepts. We have the -1, 0, and the 1, 0. So that's left 1 and right 1. We also have 0, 1, very one-centric graph. So we have points here, here, and here. Let me label my axes. This is all we need, plus the multiplicities, in order to graph this. We need the end behavior, we need all of these intercepts, and the multiplicities, and we can make this shape perfect. So we're supposed to start from the top left, so somewhere over here. And since, if you think about moving left, we're supposed to be going up and left, but now we're going right, so that means we're going down and right. So maybe you're doing it like this, or maybe it's like this. But we know we got to hit this point here, so why don't I just try and make that kind of shape from that point, like so. Maybe this is a little wider, maybe it's a little narrower. That is not what you'd be graded on for a handwritten test based on this. Now, the -1 and the +1 X-intercepts, both of those were supposed to bounce. So if I do this, if I go through it, that's crossing, that would be wrong. I'm supposed to turn around. A bounce is a turnaround, it's a turning point. Now you might say, oh, okay, well, let me just keep going straight up, hit that point and go on forever, and I'm good. No, because, all right, well, we hit the next point, but we didn't hit the one after it. So what that tells me is I should probably hit this point and then stop increasing and turn back around so that I can then hit the next point. Now you might say, well, how do you know this is the peak? How do you know the peak is halfway between them? It's usually what happens. It's not a guarantee, but I'm not going to ask you to confirm that. If this was a little higher or lower, if that point wasn't known, and we'll see that in a later example, it's not going to be an issue. So then the positive one, we were also supposed to bounce. So if we do this, that's wrong. And you can even see that it's wrong because if I do this, there's no more X-intercepts. There's nothing telling me to turn back around. I would just go down forever and it would disagree with my end behavior. So we're not going to go through that. We have to turn around. We have to bounce. Then there are no more points. If I had another point here, that would say, oh, okay, I got to go up and then come back down at some point. Maybe that's higher, maybe it's lower, but that point's not there. So I don't. I just keep on trucking upwards, keep on going, keep on going, keep on going. And there's our graph. It matches the end behavior. It hits all of the points we had to. There are 1, 2, 3 turning points, which is perfectly fine. We said there was a max of 3. So this is a pretty solid graph. Give me 10 seconds. All right, share calculator. So how can you use your calculator to tell you that you did a good job? Well, you go to your y = screen. You type in that function, which was x to the 4th, x caret 4, minus 2x squared, then plus 1, and you hit the graph button. Look at that. I'd say that's pretty accurate to what we did without using anything to guide us besides intercepts and behavior and some multiplicities. That's all we used. Now, ours looked a little wider at the ends. Doesn't matter. Handwritten, that's perfect. Everything we did was perfectly fine. Again, here is what we made. I think that's a pretty good representation of this graph. Intercepts, X-intercepts and Y-intercepts. You can't do this without them. And behavior, you need it. Turning points are just to make you feel comfortable, to make sure you didn't make too many of these little hills. You say, maybe I did this, I turned around, I did this, and I was like, oh, well, I should probably just have a couple more hills here before I go on. No, that's way too many hills. Let's try another one. Let's go with, and I want to make this one a little more fun. X plus 3 squared times x minus 5 times x plus 4 to the 2nd power. Okay, so our end behavior, part 1. This is in a factored form, so we have to approximate our function. We said that the function on the ends just behaves like ignore the plus 3, the minus 5, the plus 4, just the x's, just the exponents. So that would be x squared times x squared, which is x to the 5th, and that was a positive leading term, so that makes that a positive x to the 5th. So we have no idea what happens for now in the main section of the graph, but we know the ends. X to the 5th should look like x to the 3rd. It'll go up on the right and it'll go down on the left. Next up, and again, the order of the first 3 things is arbitrary. I just like to be consistent. Let's find the X-intercepts, which is setting the function equal to 0. Those are also known as the zeros. So we go 0 equal to, or x plus 3 squared times x minus 5 times x plus 4 squared equal to 0. It's an ugly little 2, isn't it? Better. We said when we're factored, exponents on the outside of the factor don't matter. We just set the inside equal to 0. So we set x plus 3 equal to 0. We set the x minus 5 equal to 0. And we set the x plus 4 equal to 0. But don't forget the exponents. They will be important in a hot second. That's a 0. Subtract 3 on both sides, you get x equals negative 3. But it has a multiplicity of, the exponent was 2. Whoops. And if the exponent's even, that means it bounces. X minus 5 equals 0. Add 5 to both sides. We'll get x equals 5. It has a multiplicity of, I don't see an exponent, which means it's a 1, which is odd. Therefore, it crosses. X plus 4 equals 0. Subtract 4 on both sides. You get x equals negative 4. Its exponent was a 2. So that's its multiplicity. It's even, so it bounces. Now remember, these are points. These are not vertical lines. These are points with y values of 0. So that's, for emphasis in blue, negative 3 comma 0, which will bounce, 5 comma 0, which will cross, and then negative 4 comma 0, which will also bounce. I'm going to run out of room if I do any more there. Let's show step 3 here. So this is the Y-intercept, which is finding f of 0. So that just plugs in 0 to the function. So f of 0 is 0 plus 3 squared times 0 minus 5 times 0 plus 4 squared, which is 3 squared times negative 5 times 4 squared. Was that 9, negative 45, 16? Got an extra little blurb there. Negative 45 times 16. That's negative 736. So as a point, that is 0 comma negative 736. Remember, there's no multiplicity for y-intercepts. Then finally, the last super necessary step, turning points, and again, not even necessary, but it's important for self-checking. The degree was 5. I'll even write it this time because it's not seen in the original function. It was when we got our end behavior. So that 5 tells us the degree. So the number of turning points maximum is 4. There can only be 4 peaks and or valleys. Okay, so let's see if this is enough information to get a graph. Let me grab I'm using my phone as a straight edge today. It's kind of funny. That might be a little far. There we go. There we go. X, Y. All right. Let's see. On the x-axis, we're going from negative 3 to 5. 1, 2, 3. I'll just go 5 each direction. 1, 2, 3, 4, 5. And the y-axis, well, the only number we have is this negative 736. So let's just say that the y-axis is extremely exaggerated, and just down here somewhere is negative 736. So our points are negative 3 comma 0. Oop, I want to label the numbers negative 5 and positive 5 at least. I don't want you to think that every dash is 736. So negative 3, 0 is right about here. 5 comma 0 is right about here. And negative 4 comma 0 is about here. I didn't put the end behavior up. Doesn't matter. We can do that now because you need it before you start making the graph. I don't know where to approach from. Am I supposed to come from the top or the bottom? Well, the end behavior said the left goes down and the right goes up. So again, just somewhere close to the graph and to the side, these are reminders that we should be approaching from the bottom left, and in the end, we should end up going up and right. Now let's make our graph. So we're coming from the bottom left, and the first point I have to hit, this is our goal, we have to hit that point. And we don't want it to just go straight up. That's not even straight, but you get the idea. And we probably don't want it coming in like this. This is very unusual behavior for the end of a polynomial. They're usually getting steeper and steeper. So that's why I just say in general, make it pretty steep and kind of flatten out as you get near the intercept. And that's not as flat as I would have liked it, but it's good enough. Now, at that negative 4 comma 0, we're supposed to bounce. We're supposed to turn around. So we got to come back around. You see right here, that's me coming back around. I did not go up. This is not what I did. I bounced. So basically the x-axis is acting like a ceiling, and I'm throwing a ball at the ceiling. So we come back around. Now you might say, oh, okay, we're just going to do this. Keep going down forever. Nope. You have to hit a point, and very soon. So it is very soon that you have to hit this. Now it's possible that this thing is ridiculously steep and it's going to do something like that. But we're not going to know because we're trying to do this as best as we can without a calculator. So we turn around, and then eventually we make one of those little valleys and turn back around. So something like that. Now again, it might be, we don't know exactly how low that valley happens. It might happen really quickly. It may be all the way down here at negative 500. I don't know right now, and you won't either, but that's okay. Without a calculator, we would need calculus in order to find the location of that point. And we ain't in calculus yet. Okay, so now at the negative 3, what are we doing? What are we doing? What are we doing? We are bouncing. So it's going to turn back around. So it's going to have another one of those little peaks right there. It's kind of a weird one. And then the next point we're supposed to hit, we have the intercept over here at 5, but we also have this point down here at 0 comma negative 736. And that's going to happen first. So we got to come all the way down here. So we're trucking on down. We're trucking. And we got to hit that point. Now, I don't know if that's the lowest point. I don't know if it turns around right there and starts heading back. But I'm going to say that it's unlikely. The reason I say it's unlikely is because these tend to happen halfway between two other areas. So this is a negative 3, this is a 5. That means that's probably going to happen around x equals 1. So it probably goes down a little more and then turns around to come up and hit that 5. Now again, handwritten test, that is not a particular aspect I would grade you on. If someone turned around at that negative 736, I would give them full credit. What I'm looking for is, did you do the intercepts? Did you do the end behavior? Does this look like a polynomial should basically? Did you get your bouncing and crossing correct? That's what I'm looking for. Then from the 5, we were supposed to cross. That says cross right here at the positive 5. So we do not turn around. We keep on going through. There are no more points for us to hit, so we just keep going up, getting steeper and steeper, and it matches the end behavior, so that's a good sign. I didn't put an arrow on the left one, the left side right here. But it should be there. So there's our graph. Again, we started with the left end behavior to tell us where to approach from. We hit our intercepts and pay attention to their multiplicities, whether we're supposed to bounce or cross. We try and hit the next point, which tells us when we might have to turn around or when we keep going. Then we had this point, so it said, oh, we got to drop way down. And like I said, wherever you make that valley, somewhere in this region, I would not grade on that particular aspect as long as you hit the point and you turn around, you hit that, and you keep going and you match your end behavior. I didn't use any symmetry. I will say that problem A, let's go back for a second. If you look at this picture, that really looks like it's symmetric about the y-axis, and it is. This graph is symmetric about the y-axis. If you did the symmetry test, this function is even, and look, it's only got even exponents, so that's a good sign that it's probably even. What that means is you could have just drawn the, if you identified that symmetry, you could have drawn the left side and then just mirror imaged it and you're already done. But there is definitely no symmetry in the graph we just created. Wrong button. That was new page, not go forward. No symmetry in that graph. It's not even, it's not odd. It's an odd graph in that it's curious, but it's not an odd function. All right. One more sounds good to me. C, black. F of x equals x to the fourth minus 9x squared. So all those steps. First, end behavior. This is not factored, so we can just identify the biggest exponent, which is a 4. That's even, which says the ends will go in the same direction. Since it's a positive x to the fourth, that says they both go up. If that had been a negative x to the fourth, they'd both go down. So again, no clue what happens in the middle, but we do know both ends go up. Next up, let's grab the X-intercepts by setting the y equal to 0, also known as the function equal to 0. So that's x to the fourth minus 9x squared equals 0. This is factorable. There's a GCF of x squared. So let's pop out an x squared, open a parentheses, divide it. That'll give us x squared minus 9. X squared minus 9 is factorable. That's a difference of squares where your a is x and your b is 3. So this is x squared times x plus 3 times x minus 3. And that'll be equal to 0. And then we can use our zero product rule. Set each factor equal to 0. Now x squared, that's an exponent on a factor. So we really just need to focus on the x. The 2 is its multiplicity. So we get x equals 0, x plus 3 equals 0, and x minus 3 equals 0. The first one solved, x equals 0. The second one, subtract 3 on both sides, you get negative 3. The third one, add 3 to both sides, you'll get positive 3. But we need their multiplicities so we know whether they're bouncing or crossing. Just the 0 is not good enough. This is a critical element. The exponent of the first one was a 2. That's even, so it will bounce. There were no exponents written for the others, so they assume to be 1s, which means they cross. Has nothing to do with the fact that the solution was odd. It has to do with the fact that an exponent on the factor was odd. So these 3 points, we have x values of 0, negative 3, and positive 3. So that's 0, 0, the origin, negative 3, 0, and positive 3, 0. Those are our x-intercepts. Now, because this first one is the origin, I know what my next bit of information is going to be. I know that the y-intercept is 0. But I'll show you why that is. So f of 0 is 0 to the fourth minus 9 times 0 to the second, which is 0 minus 0, which is 0. Therefore, we get the point 0, 0. The same point as what we found from doing the x-intercepts. That can happen. An origin is both an x and a y-intercept, so if you find it one way, you're going to find it the other way. And this is going to happen more and more frequently as we progress. So you might think we got 4 points, but in reality, we only have 3. Maybe that's an issue, maybe not. And if it doesn't feel like it's enough points, then we just go and get more points by plugging in an x value we know. Not that we know, an x value that we like, that we haven't already used. Finally, the fourth step, the number of turning points maximum would have to be 3 because the degree is 4. If the degree is 4, you can only have 3 turning points. It's always 1 less. So that should be enough. Let's make our graph. Using technology to technology. Thank you, cell phone. So we have x values going from -3 to 3. So let's go 1, 2, 3 in each direction. 1, 2, 3 in each direction. Left and right. The y values, we didn't even get any. So maybe just do 3 every direction for good measure. I'm seeing if there's a way I can do a handwritten portion of this next test and have it not just be entirely my math lab. I'm trying to figure out the dynamics to that. So please make sure that you can do this by hand as well as how you do it in my math lab. In my math lab, you have to go and input all these little bits of information, and then I believe they give you a multiple choice option for the graph itself. All right, so our points, 0, 0, which we saw happen on 2 different occasions. We found it 2 different ways. The -3, 0, and the +3, 0. I feel like something's missing on this graph. What might it be? What might it be? The end behavior. The end behavior said both ends go up, so I'll just put a little arrow on the outsides reminding me that that's what should happen. It didn't matter if I plotted the points then the end behavior, or the end behavior then the points, as you can see. So we're supposed to start from the top left, maybe over here, and then we got to hit this point eventually. That just doesn't seem probable. Polynomials tend to grow really quick on the outsides. So it's generally steeper, generally something like that. And again, maybe it's not bending as much near the -3. Don't focus on that aspect. So at the -3, what do? We cross. So we go through. Now you might say, well, do I just keep going down forever? Do this and then eventually come up and like that, right? No, that would not be it. The points tell you when to start coming back around. So we're supposed to hit this point at the origin. So it's probably going to look something like this. Maybe it's a little steeper. Maybe it looks something like this. I don't know. It's tough to tell without getting more points. I tend to make more flatter assumptions. But it is an assumption. Do I know that this thing valleys off at -1.5? I absolutely do not know that. It's another assumption. But again, those are not things I'm grading on. At the origin, we're supposed to bounce, so we come back under, like so. And then we're supposed to hit the next point, so I bet I should probably make it look very similar to the left side. It feels like this is an even symmetry. And in fact, there's only even exponents, which is a good sign that this is even symmetric, which means the y-axis is a mirror. All right, at the +3, we're supposed to cross. So we go through, and there's no more points to hit, so we're going to keep going up forever and ever and ever, something like that. Now this kind of changed how I flattened out here at the -3. I just did the same thing here, but it's not really a great idea. Because this wasn't the lowest point, it shouldn't have flattened out so quick. But again, that's not something I'm grading you on. What I'm trying to say is this picture probably would have looked more like this. That's a slightly better picture in my opinion. but that's a -3, and that's a +3. So that's something you may even want to do, is just go back and flesh things out. You don't usually have these weird little bumps along the way of polynomials. And I'm not saying you never do. You can. I'm just saying the ones that we will graph usually don't. So again, you can make a note that this was an even function. You could plug in -x and you'll get the same thing, which means once you draw the left half, you have the right half. Now, maybe you don't trust yourself. Maybe you want to go to your calculator back to the graphing screen. Let's clear it. We had, what was it, x to the 4th minus 9x squared. We graph it. And I'd say that we did a fairly decent job. The only aspect that we goofed, but again, I would not discount, I would not take points off, is, remember I said maybe the section from -3 to 0, maybe it wasn't that flat, maybe it was more extreme. It turns out it was more extreme. But again, a student who gave me this as a handwritten answer, that would be perfect. This would get full credit because you've done everything you can without just going and plugging in a bunch of x values. And that's not how we want to be graphing. We're trying to avoid just plugging in random x values. I'm not saying we can always avoid it, but we only need a couple, not 10 or 12. Maybe you don't trust that previous graph. This one seems a little wackier, so maybe we should check that in our calculator. X plus 3 squared, x minus 5, x plus 4 squared. Calculator, y equals clear. So that's x plus 3 in parentheses. I hate doing this with a mouse. I think it was squared. Yes, times x minus 5 times x plus 4 squared. Go to graph. And, well, that's weird. I don't see that whole picture that we had. You can see right here that we hit that intercept, then we turn back around very quickly. This is a very small valley. We hit the next intercept, then we shoot down. So down here somewhere, we're hitting that -736, and then at some point we turn back around. So if you want to see this in grand detail, what I can do is change the window. I don't really need to change the x scales, but I do need to change the y's, not scale, the min and max. So the y minimum, we had a -736 up there, so let's put it at like a -1,000. And the y maximum of 10, maybe that'll be good enough. All right, so now we can see it going up. We can no longer see the detail of that little bump anymore happening right here, but that's because we are zoomed way, 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 way out. But we can see that it comes down, it hits that -736 somewhere. If I actually type in, if I hit trace and then 0, that says -720. Where did I get -736 from? Maybe I typed a number wrong somewhere. No, it's 720. I don't know why I got 736. I must have typoed on my, well, no, I did it in my head. I must have screwed up in my head. That's all right. Will it matter how we graph the equation in my math lab? Your math lab or my math lab? Whose? No, I'm just kidding. In my math lab, as I said, it's multiple choice. You are not going, my math lab is not complex enough to be able to do this by hand. It's just an A, B, C, D option. But again, before you get there, it's going to ask you, what are the intercepts? What's the end behavior? All that stuff will be accounted for. All right, so sorry about that simple goof. I'm going to blame it on multitasking. So -720, but you can see that that was not the minimum. It keeps going down, it keeps going down, it keeps going down. If you really wanted to be able to see it, we'd have to zoom out even more. Let's make that y minimum maybe -2,000. Nope, that's still not even far enough down. Let's make it a -3,000. This is just for fun right here. I can almost see it. Maybe 3,500. Almost. I should have just done 4,000. I had a feeling. There we go. Now we can see it. So again, you still can't see the teeny little bump because we are zoomed way out. You'd need a microscope probably to be able to see that teeny little bump there. But you can see that that point was not even close to being the minimum. It happened way over here. In fact, it did not happen at +1, like I said, would be probable, but probable does not mean guaranteed. It actually happened over here at like 3.5. If you trace this out, we can see it happens around, yeah, 3.4, 3.5, something like that. But I don't have a way without using calculus to find out exactly where that is. And we're not in calculus, so that's a non-issue. All right. So with that being said, that'll finish up 3.2, graphing polynomials. New share screen. 3.3, dividing polynomials. This is something that you were supposed to have learned in your developmental math, either in Algebra 2 or in MTE. It's either 7, I think it's 7, yeah, 7. But it's also one of those things that we know a lot of people forget very easily, so we readdress it. It just seems like most of the readdressing stuff was done earlier in the semester. No matter. So let's just focus on this for now. Goodbye, synthetic division. We'll get to that later. And by the way, there are 2 types of division that we'll learn in this course. Long division, which again, you arguably may have learned already. You may even remember it if you're lucky, but we'll discuss it. And then synthetic division. Synthetic means, it kind of means like, I don't want to say fake, but like an alternative, a workaround. Like you have synthetic oil, there's something different about it versus regular oil that's a little better. But a lot of people will use the word synthetic to describe better. It doesn't always mean better, but I would say it means better most of the time in this course. So I'm going to teach you long division, and we'll do like 2 examples with it, and then you'll never see me do it again in class. I'm not saying it won't be a test question, and if it was, I'd only give you 1. This is me. I've got my finger pointing up in a 1 motion right now to be emphatic. I would only give you 1 of these on the test. Synthetic division is amazing. For what purpose we have, synthetic division is amazing. Synthetic division does not always work. It requires a special case. But the thing that we're going to need it for, it's always under that special case. You're going to see these long division problems are going to take up a lot of space. They're going to take a decent amount of time. There's a lot of little bookkeeping. It's a pain in the butt. Synthetic division, we're going to compress the space a ton. We're not going to write any X's for the whole problem, for the work of the problem. It's just going to be numbers. And it's just 3 steps that you memorize and do over and over and over. All right, so before we get to synthetic division, what exactly is this long division process? It is literally the same process as for dividing plain Jane numbers. Think about if I asked you to do 22 into 504. The 3 steps would be divide the 22 and the 504, which would be twice. Now, it can't go in the 5, it goes in the 50, so you put it over the 0. Then you multiply. The 2 times the 22 is 44. So you take the 2, when we divided, the 22 only went into the bits that you had to. I didn't even look at that 4. You just use what you need. But when you multiply it by everything on the left. And then what do you do here? You subtract. And you'd get 6, and you'd continue on and on and on. I don't care what that answer is. It's 20 something, 22 point, I don't know, 8, 9, whatever. Notice that says the same things here. Divide, multiply, subtract. Divide, multiply, subtract. Same 3 steps. But it's going to be a little more complicated because you're not just dealing with numbers, you're dealing with polynomials, x squared, x cubed, x to the 4th. So I need to be a little more specific with my words. First of all, pretty much like any polynomial, you need these suckers in descending order, or it's going to make a lot of things impossible. You also have to make sure all terms are accounted for. So you may have like a 0x squared or a 0x cubed or a 0x or even a 0 somewhere. Think about this. If I had the number 22 dividing into 504, could I just write 22 into 54? Is that the same problem? No. You need that 0 to represent the tens. Polynomials, instead of having places, they have powers. You need all of those powers accounted for. You need to see the position for the x's. You need to see the position for the x squareds. So if you don't see them, you need a 0 in their place, a 0x squared or a 0x, and I promise we'll do an example with it. Then you multiply whatever you get up top by everything on the left. Multiply the result by both terms on the left. And I say both, but it could be more than one. I mean, excuse me, more than two. But we just only see two terms. Then you subtract, and I put it in air quotes. I just said air quotes. I put it in quotes. I'd be doing air quotes if I was in class. By changing all bottom signs and then combining vertically. So up here, we were supposed to do 50 minus 44, but these are going to be things with x cubes and x squareds. Just writing a minus in front of that isn't going to be enough because we're supposed to subtract the whole thing. So to show us subtracting, we just change the signs because changing the signs is equivalent to subtracting. Adding a negative is subtracting a positive, right? Then you bring down the next term, you repeat as necessary. Now this thing right here, let me write this in actual math speak. In fraction form, f of x over d of x. So this is just saying if we got a function and we're dividing it by something, d of x is saying the denominator. So we got something divided by something else. The answer is always going to be the quotient, q for quotient, plus r for remainder, and the remainder can be a function. It's usually a number, but it can be a function, over the original denominator. So again, that is quotient plus the remainder over the original denominator. Do you know why we call it a remainder? Because it remains to be divided. We didn't actually divide it. That's the whole reason we call it a remainder. The quotient, we are actually going to have divided it out. But then usually there's some junk left over and we can't introduce decimals to polynomials. That wouldn't make sense. So we just leave it to the side, but we make sure we leave it over the denominator. Divide, multiply, subtract, divide, multiply, subtract, divide, multiply, air quote, subtract. What I like to say is draw the line, switch the signs. So let's try this out. New share, whiteboard. All right, so 3.3, example 1, use long division, and A, we'll do x cubed plus x squared. I had the 3 in my head. I still have the 3 in my head. Writing in multitasking is fun. Plus 3x minus 10 divided by x minus 2. So use long division, and if I give you this type of problem on the test, if I say use long division, you're supposed to use this technique. And once again, I would only ask you for one of these one time. I will never ever in a pre-calculus class give more than one long division on a test ever in my life, because it's not what we're supposed to be using moving forward. All right, so you got to put this in the right notation, which means the x minus 2 goes on the left. All terms are accounted for, x squared, x constant, so x squared plus 3x minus 10. So first step, divide. Remember, it goes divide, multiply, subtract. For the division, we're only looking at the leading terms. We're only looking at the leading terms. We're saying how many times does x go into x squared? How many times does x go into x squared? And I know that sounds like a weird question. how many times is x going to x squared? Don't think about it that way. Go to the side and just write the inside one over the outside one. This is saying how many times is x going to x squared? Well, just subtract the exponents. 2 minus 1 is 1. It reduces to an x. Now, because that is an x to the first, I want to put it in the x to the first column. I do not put it over the x squared. I put it over the 3x. So that was the division step. For the multiplying step, we take this and we multiply it by everything on the left, the x and the -2. So the x times the x is an x squared. The x times the -2 is a -2x. Make sure you're putting these in appropriate columns. Now I'm going to do something before I quote subtract. You really want to see the original signs of these. It's obvious that the 2 is negative. This x squared was positive, and we normally never write this. But for the first time, maybe even in your life, I want you to write that positive as a positive sign. It is critical for your notes. It's not critical right this second. It's critical in a couple of weeks when you're studying this stuff and you go, why is there a minus sign there? That's a positive when I do the multiplication. What was wrong with Mr. Beckner? What was wrong with me? No, it's because this is going to change. That's why we're putting the plus sign. So we said in the instructions we're supposed to subtract, which meant to change the bottom values signs. So this positive x squared becomes a negative x squared. This -2x becomes a positive 2x. This green is us changing the signs so that we can quote subtract. Then you just add vertically. Don't use the blue, use the green. So x squared minus x squared cancels. And that's something that should always happen. The first pair will always cancel. The second pair, it may not, it usually doesn't. 3x plus 2x, that's a 5x. And you can write the plus here if you want, but it's not mandatory. It's only mandatory for the multiplication step. Then you bring down the next term, maybe the next pair of terms if this isn't going to give you something completable, but it usually does. And then you, as your Spanish teacher would say, repita, por favor. Repeat, please. Divide, multiply, subtract. So for the division, that's where we'll go to the side, we're only looking at the leading terms. Now, we're not looking up here, we're down here. So the x and the 5x. That's what we're dividing, and it should be the 5x divided by the x. 5x divided by x is 5. Now, we can't just put a 5 up top over the -10. You need that plus sign to show the separation. Otherwise, it looks like x times 5. Then we multiply. For the multiply, we're just taking the 5 times the x and the -2. 5 times x is 5x, but we will want to write that positive. 5 times -2 is a -10. It's got a sign, so we're good. Draw the line, switch the signs. This is us subtracting. Now, I'm not switching the black numbers, the top number signs. I'm just changing the blue one, the bottom one. So that positive 5x becomes negative. The -10 becomes positive. Please do not think these always are positive negatives turning negative positive. They both could have been positive, turning both negative. They could have both been negative, turning both positive. It's just a coincidence. All right. 5x minus 5x. 5x minus 5x, using the green, not the blue, cancels. -10 plus 10 also cancels. There's nothing else to bring down, which means we're done, but we can't just leave this blank. That means that's a 0. And this is the remainder. The x plus 5 is the quotient. So the answer, remember it goes quotient plus remainder over divisor. Again, quotient plus remainder over the original denominator, D for denominator. The quotient's x plus 5. It's the red right here. Then a plus. The remainder was 0 over the original denominator's x minus 2. And then this is where I go, class, does anyone see something I don't need to write? Well, 0 divided by anything is 0. You don't want to write this. You just want to write this as x plus 5. If the remainder is 0, that means it divided perfectly. It also means something very awesome that we'll get into in a little bit. Now, I want to point out something with this problem. I can fit it here. Well, I didn't mean to write over that x. Undo. Da, 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 da. Let's go back to the original problem, and maybe you happen to notice something. Maybe you notice that the top is factorable. So, oh, okay, factors of 10 that subtract a 3 are 5 and 2. So you go x2, x5 to make sure they combine to a positive. It's a positive and a negative, positive 5, negative 2. And then that's over x minus 2. Holy cow, look at that, x minus 2 top and bottom. Well, they just cancel, and the whole thing is x plus 5. The same answer is what we got. And then you go, Mr. Beckner, why would you do this to us? Why would you give us a problem that we could have knocked this out in arguably 10 seconds if we know how to factor and cancel? Because guess what? In the real world, only about 2 to 5% of these actually factor and cancel. Most of them don't. And that's going to be a much more common scenario for us now. Yeah, if they factor and cancel, that's awesome. If you recognize it, then you could take a shortcut and cheat the system, especially since my math lab would just tell you the answer's right anyways. But it's still an important technique because, again, in the real world, 2, 3, 4, maybe 5% of these actually have this happen. Right, let's do another one. But if they do factor and cancel, it's very cool. It implies something very awesome that we'll need moving forward. B, let's go with 12x squared plus x minus 4, and let's divide that by 3x minus 2. Before I complete this problem, I want to mention something. A and B are very different. Oh, there's a 12 on the top. That's not why. It's the 3 in the bottom. This 3 right here means we can't use synthetic division. I haven't talked about what it is yet or why we can't, but I'm just telling you up front, because that 3 is there, you can't use synthetic division. However, with example A, there is no 3 in front of the x, it's just x and then a constant. You can use it on that one. So A is a much more common type of problem that we'll see in this course. We will never see this B problem again in the rest of the chapters, I can promise that. All right, so again, just wanted to mention that. So let's set up the division. All the terms are accounted for, they're in descending order, so we put the 3x minus 2 on the left, the 12x squared plus x minus 4 on the right. I'm going to go a little quicker this time. For the division, again, we're looking at just the leading terms, the 3x and the 12x squared. If you need to go to the side, that's 12x squared over 3x. 12 divided by 3 is 4. You'll lose a factor of x. Since that's a 4x, not 4x squared, it goes over the x in the quotient. Then you multiply. 4x times everything on the left. 4x times 3x is 12x squared, but we know we want to see its original sign. That's positive. 4x times negative 2 is a negative 8x. Then we draw the line and we change the signs. So the positive becomes negative, the negative becomes positive. The first terms, when you combine vertically, will cancel. That should always happen. If it doesn't, you've made a mistake somewhere, I guarantee it. Then x plus 8x is a 9x. Bring down the minus 4. Repita, por favor. Divide the 3x into the 9x. So if you need to go to the side, that's 9x divided by 3x, which is positive 3. I can't just write 3 here. You got to write plus 3. You okay, buddy? My dog's coughing. All right. Then we multiply. Again, the 3 times everything on the left. We already multiplied out the 4x. It's just the 3. How are we on time? 2:40. 3 times 3x is 9x, but we know we need that positive there. 3 times negative 2 is a negative 6. Draw the line, change the signs. It's the wrong color, green. So that's a negative 9x now and a positive 6 now. Combine vertically, The first one's canceled. 9 minus 9 is 0. Negative 4 plus 6 is positive 2. There's nothing else to bring down, so that's the remainder. The 4x plus 3 is the quotient. So the remainder is not 0 this time, which means there will be a fraction left. So we go quotient, 4x plus 3, then plus the remainder of 2 over the original denominator. The denominator doesn't change, 3x minus 2. And that's our answer. Please notice that the answer is not 4x plus 3 plus 2 all over 3x minus 2. This is very, very wrong. The remainder is what remains over the denominator. The quotient has been divided. We divided the 4x out. We divided the 3 out. So be careful there. Let's do one more that's a little beefier. C. This will be the last long division we ever do together. 4x to the 4th plus 6x minus 4x squared all over x minus 4. This one needs to be rewritten as 4x to the 4th plus 0x to the 3rd minus 4x squared plus 6x plus 0. There was no x to the 3rd term, but we need to see it. There was no constant term, but we need to see it. These are placeholders. That's like having the number 507 and not writing the 0 without those. So that's our top. The bottom is x minus 4. You might say, well, where's your x to the 4th, x to the 3rd, x to the 2nd? That doesn't matter. You only need the leading term down in the top or bottom respectively. So I'm going to go over here because I'm going to need a decent amount of room for this one. X minus 4. That's going to be a little high. It might not look that high to you, but I have toolbars on the menu you can't see, I think. So then 4x to the 4th plus 0x to the 3rd minus 4x to the 2nd plus 6x plus 0. Again, without those 0 terms, you will make mistakes. I will 100% guarantee that. I have never seen a student miss one of those and get an answer right. Not in my life. I don't even think I can do it. I don't try though. So x into 4x to the 4th. Again, if you need to see that stuff, let's go to the side. That's 4x to the 4th divided by x, which is 4x to the 3rd. That's a terrible looking x. Put it in the x to the 3rd column, which would not have existed without that 0 there. You probably would have put it over the x squared, and then you would have started messing things up already. Then we multiply. 4x to the 3rd times x is 4x to the 4th, but we want to see that it's positive. 4x cubed times negative 4 is a negative 16x to the 3rd. Draw the line, switch the signs. That's us subtracting. So that's now a negative and a positive in that order. 4 minus 4 cancels. Those first pair always cancel. 0 plus 16 is 16. So we get 16x cubed. Bring down your next term. As I said, in crazier examples, you might need to bring down the 6x as well. But I'm not giving those examples. I will not test on those examples. Now the division, x into 16x cubed. So 16x cubed over x, you lose a factor of x, so 16x squared. But you can't just write 16x squared in the top. You need the plus sign. Multiply. 16x squared times x is 16x cubed. We need the plus sign. 16x squared times 4 is a negative 4 that is. 64x squared. Draw the line. Change the signs, negative, positive. First pair cancels. Negative 4 plus 64 is going to give us 60. So that's 60x squared. Bring down the plus 6x. And we just keep going. X into 60x squared. 60x squared over x. That is a 0. That would be 60x. So plus 60x in the quotient area. Then we multiply. 60x times x is positive 60x squared. We need that plus sign. 60x times negative 4 is going to be negative 240x. Draw the line, switch the signs. Again, this plus minus become a minus plus is just a coincidence that I keep doing that. The 60x squareds cancel as they should. 6 plus 240 is 246 with an x. Bring down the plus 0. Some people would argue you don't need that because it's nothing. They're right, but you should just have that habit anyways. Divide the 246x by the x, which is positive 246. So a little plus 246 here. Multiply. 246 times x is positive 246x. 246 times 4, that's 984. Let me double check that since I goofed on an arithmetic earlier with numbers like that. 250 times 4 would be 1,000. Subtract 16 is, yep, that's 984. So minus 984. Draw the line. Change to subtraction by changing the signs. The first pair cancels. 0 plus 984 is 984. There's nothing else to bring down, so that's a remainder. So our answer is the quotient, which was red. 4x cubed plus 16x squared plus 60x plus 246, then plus the remainder of 984, not all over, just the 984 is over the denominator of x minus 4. There we are. So again, very awesome technique, very useful technique when you're just dividing two random polynomials. But in pre-calc 1, the type of problems that we're going to be focusing on, the denominators will always be this very special format that's just an x and a plus or minus a number, like x minus 4, or x plus 2, or x minus 17, or x plus 30. You're not going to see any x squareds in the bottoms. You're not going to see any coefficients of the x's. And those are the conditions for us to be able to use synthetic division. So synthetic division is not for any f of x divided by any denominator. This is only for a function divided by x plus or minus a number. That's the only way this works. It can be x plus a number or it can be x minus a number. But notice that this right here says to divide by x minus c. This is another one of those things that's going to keep flip-flopping signs on us, kind of like shifting, or kind of like the vertex for the x-coordinate of a vertex for a quadratic. And that one being positive, one being minus, that theme's going to stay with us for a while. So if your denominator is of this very special format, this is the process you're going to do. You're going to write c, whatever the number is, in a half box. Now, if it says x minus, let's say 5, that makes the c 5. If it said x plus 5, that would make it a negative 5 that goes in this little half box. What do I mean by a half box? This is what I mean by a half box. It'll look like that. Then you'll write the coefficients of the original function of the top, when I say function, to the right of the box. So your coefficients go to the right of that. So a 3, a 1, a 0, a 2, whatever numbers they are. Then you will, hold on, let me give myself a little more space for that. So you put your c in a half box. You have some coefficients over here. Let's say just number 1, number 2, number 3, number 4. You're going to leave a blank row. You're going to leave a little blank here. So you leave a blank row below and a plus sign. Put the plus sign under your half box. So this is the setup for synthetic division. If your denominator is x minus a 5, you have a 5 in this box. If your denominator says x plus 5, you have a minus 5 in this box. You do not change the signs of the coefficients. They just go in place based on descending order. And if any terms are missing, you'd need zeros there. That will be a common theme. And then this is what you do. What these 3 steps right here do is they compress the dividing, the multiplying, and the subtracting aspect of long division in an unbelievably quick manner. But it only works if there's no coefficient of x, if there's no x squareds in the bottom. You bring the first number down, and I should point a little lower than that. You're bringing the first number down below the line. That's just automatic. You bring it down. Then you'll multiply that value by the number in the half box. So you'll multiply, so that little dot saying multiply whatever's here by the number in the half box. And then that goes here. The product goes there. 1 column to the right. Then you just combine vertically. You take this number and you add them. So you add vertically to get that. And then you just keep doing the same thing. This number gets multiplied by the c. It goes 1 column to the right. You add. Multiply by the c. 1 column to the right. You add. That is going to get you every number you need for the answer so insanely fast in comparison to long division. And it seems weird. It seems wacky. I hated this at first. The first time someone introduced synthetic division to me in high school, Algebra 2, I think, I was like, what's the point of this? The point is, we take a problem that normally takes us 5 to 10 minutes, and we turn it into a problem that only takes us 1 minute. Because we're going to have to do this over and 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 over. Long pause and over. All right, so what does this do for us? You're going to have a bunch of numbers at the bottom. The numbers on the bottom are the coefficients of the quotient, except the very last number is the remainder. Again, the numbers on the bottom are the coefficients of the quotient, with the last number being the remainder. So we had our c and a half box. We had some numbers up here. We left some space. We multiply and added until we get some numbers here. Let's, I don't want to use the same representation again. I will. It's a different. These are not the same numbers as before. So we got number 1, number 2, number 3, number 4. They're not always 4 of them. It could just be 3 of them. It could be 17 of them. I'm just giving a particular example. The far right number is the remainder. The one to the left of that is the constant. The one to the left of that is the coefficient of x. The one to the left of that is the coefficient of x squared. Again, these are coefficients. I'm not saying that x squared is that number. I'm saying that's the number that goes in front of x squared. You can keep going. There could be a 5th number, then you'll have an x cubed term. You could have a 6th number, then there'll be an x to the 4th. I think I said something wrong. If there's a 6th number, there would be an x to the 4th. Okay. So what we're going to do is we're going to go back to example 1a, which we already know the answer to, and we're going to do it again, but we're going to do it with this synthetic division. So keep this process in your head. Hopefully you wrote it down. We're supposed to be writing all these things down. The c goes in a half box, which will change signs. The coefficients of the top go to the right. Leave a blank row, bring the first number down, multiply, add, multiply, add, multiply, add. And then your answer is based on that final row. From far right, that's the remainder, then the constant coefficient, the x coefficient, the x squared coefficient, the x cubed coefficient, until you run out of terms. All right, whiteboard, new page. What are we up to? Example 2. Use synthetic division. X squared plus 3x minus 10 divided by x minus 2. So again, we know the answer for this is equal to x plus 5. Let's just keep that stored to the side. The bottom is of the very special format x plus or minus a number. There's no, if I have a 3 right here, you can't do it. This synthetic division fails. If this was an x squared, synthetic division would fail. It has to be just an x, and just a number being added or subtracted. So because this says x minus 2, that tells us that c is 2. And it doesn't have to be c. I'm just giving you a letter, an arbitrary letter for it. It's a constant, c for constant. That is the number that goes in that little half box to the side. Because that says minus 2, we put positive 2 in the half box. To the right of that go the coefficients of the top. X squared, x constant. All terms are there. They're all in the right order. So we go 1 for the x squared, then 3 for the x, and then negative 10 for the constant. We leave a blank row, put a little plus sign under your 2. And then it just goes, bring the first number down, then multiply, add, multiply, add, multiply, add. Remember how that process was supposed to go divide, multiply, subtract? When we change the sign of the C, that handles the subtraction for us. That changes all the signs after the multiplication, believe it or not. So that's why we changed that sign. So we bring the first one down, bring the 1 down. I want to show my work in red. So we bring the 1 down. Then we multiply this 1 times the 2. 1 times 2 is 2, and that goes 1 column over in the blank row. There's always going to be a blank spot in the very first column because that just gets brought down. And then you add. 3 plus 2 is 5. Again, 1 times 2 is 2. That goes here. Then you add. 3 plus 2 is 5. The addition part should be painfully obvious where the 5 should go. Then you do it again. 5 times 2. Again, bottom number times the C. 5 times 2 is 10. Again, that 10 came from multiplying the 5 and the 2. And then you add. Negative 10 plus 10 is 0. That's it. From right to left, the 0 is the remainder. The 5 is the constant. The 1 is the coefficient of the x. So that says that our answer is 1x plus 5. And then if you go plus 0 over the denominator of x minus 2, once again, we don't really need to see that part. We don't need to see the 1 in front of it. We get x plus 5. And guess what? That is the same as what we got before. Now, this was the very first one we did. It only took us 3 minutes. If this was the 100th one you've done, which you will do more than 100 of these in this course, you better believe me, if you're actually doing the work. I really hope you are. That problem, someone can knock out in about 15 seconds with practice. I know I can, but I've also done it more than 100 times. I've done it thousands of times. But it's definitely understandable that most people can knock that out in under a minute with practice. If it's the first time you've done it on a test, it's not practicing. You're not doing what you're supposed to do. So x plus 5 is the answer. Again, all I did was write a bunch of numbers and multiplied and added. That division algorithm for long division, as long as that leading coefficient is 1, it breaks down into this much simpler idea that with practice is very efficient. Let's do another one, and let's do one we haven't seen. X cubed minus 5x squared plus 7x minus 2, all on top of x plus 4. That's an x plus 4 in the bottom. That is of the format for synthetic division. I wouldn't tell you to use synthetic division if you can't, first of all. So what goes in the half box? Is it the 4 or is it a negative 4? Think back. We're supposed to change its sign. So we put a negative 4 in the half box. To the right of that go the coefficients of the polynomial on the top. Make sure they're all accounted for. X cubed, x squared, x to the first, constant. We're good. Make sure they're all in descending order. We're good. So x cubed has a 1 in front of it, then a minus 5 in front of the x squared, a positive 7 in front of the x, and a minus 2 for the constant. Leave a blank row, plus sign in front of it. Get red for my work. Bring down the first number, the 1. Multiply, add, multiply, add, multiply, add. Multiply the 1 by the negative 4. Negative 4 is always getting multiplied. So 1 times negative 4 is negative 4. Add negative 5 plus negative 4 is negative 9. Watch your arithmetic. Very easy to make simple mistakes, of course. Don't rely on calculators to do this baby arithmetic for you. Use your brains. -9 times -4 is going to give us a positive 36. Then we're going to add 7 and 36, which is 43. Then we multiply. 43 times -4 is negative, what's that, 172? Yes? Yes. Then we'll add -2 and -172 is -174. That's it. We just did the whole division. So our answer lies at the bottom. From right to left, that's the easiest way to identify everything. That goes remainder, constant, coefficient of x squared. If there was another number, coefficient of x cubed. So our answer is 1x squared. 1x squared. I don't really need to write the 1, do I? No. So let's not write the 1. Just showing you for demonstration where it came from. Do we put in placeholders like division? Yes, and we will see an example with that. So again, the 1x squared, I chose not to write the 1 because it's unnecessary and would be wrong in my math lab, of course. Then the -9, that's the coefficient of the x. Then the plus 43, that's our constant. I can't just write 43, I need the plus. Then the remainder is negative, so instead of going plus -174, I'm just going to go minus 174 over the original denominator of x plus 4. Again, that shortcuts the amount of work, time, and effort on long division by a factor of 10. A problem that would take us 10 minutes can now take us only about 1 or 2 minutes. And again, the reason we love synthetic division is because you are going to have to do this over and over and over and over and over and over and over in this course. All right, so someone asked a question about, do we use placeholders like in long division? The answer I said was yes, and we will see an example of that right now. And in fact, we will dig up an old example. For our C, we will do problem C from 1. So that was 4x to the 4th plus 6x minus 4x squared all over x minus 4. Now I'm going to pull out red for wrong for a second, and I'm going to erase everything in just a second. Oh, okay, so the bottom fits the format. It's a -4, so I put a +4 on the left. Again, all this is going to be wrong. And let's see, I see a 4, then I see a 6, and then I see a -4. And you would do this. And let me show you why this is wrong. Again, you don't have to write this, but this is why it's definitely wrong. We know the answer from before. It was supposed to have a remainder of 984. I remember that specifically. So let's just see what would happen if we did this. That's a 4. 4 times 4 is 16. 6 plus 16 is 22. 22 times 4, that's 88. 88 minus 4 is going to give us 84. So that says that's the remainder, the constant, and then the coefficient of x. So the answer is 4x plus 22 plus 84 over x minus 4? Question mark, question mark, question mark. No, very wrong. Very, 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 very wrong. If you go back a couple pages on the whiteboard, where's my mouse? It's so hard to see sometimes. The answer was 4x cubed plus 16x squared plus 60x plus 246 plus 984. So we get this wrong for several reasons. Reason number 1, we're missing an x cubed and a constant. We didn't account for that. Reason number 2, the 6x and the 4x squared are in the wrong order. This is terrible. Goodbye, terrible. So we have got to set everything up in the right order and use placeholders just like before. So let us rewrite as 4x to the 4th plus 0x to the 3rd minus 4x to the 2nd plus 6x plus 0 on top of x minus 4. Now let's do our synthetic division. So we put a +4 on the left because this says -4. Then to the right of that go the coefficients in descending order based on the power. So 4, 0, -4, 6, 0. Not only do we have 2 additional columns, we've also swapped the order of the -4 and 6. Believe me, that makes a difference. Most common mistake people screw up with synthetic division is they miss the missing terms, and they're going to get an answer that wouldn't make sense, and I'll explain why after the fact. All right, so bring down the first one, red in the work in red. So bring down that first 4. Then multiply, 4 times 4 is 16. Add, 0 plus 16 is 16. Multiply, 16 times 4 is 64. Add, negative 4 plus 64 is 60. Multiply, 60 times 4 is 240. Add, 6 and 240 is 246. Multiply, 246 and 4 is 984. Add, 0, 984 gives you 984. These are some familiar looking numbers. Look how quickly we got them though. That was insanely fast. Okay, yeah, I did the multiplications quick, but again, you would still be able to do that way faster than previously. From right to left. Remainder. A lot of people will forget that that's the remainder. It's not the constant, it's the remainder. Then constant, coefficient of x squared, and then coefficient of x cubed. So therefore, we can see that our answer is 4x to the third, the red and the blue combined, plus 16x squared, plus 60x, plus 246, plus 984 over x minus 4. And that is the same answer we got before, but in a drastically reduced amount of time. Amazing what this technique can do for you when it works. But only if you know how to do it. Only if you know when to do it. And again, any problem moving forward in the later sections, these bigger concept problems, in the solutions of them, we are going to have to be doing, I don't know, maybe 2 or 3 or 10 synthetic divisions. Depends on our approach. Let's keep practicing. Let's do another fun one. And you know what I mean by fun, right? X to the 7th minus 128 divided by x minus 2. Again, x plus or minus numbers in the bottom, so it works. It's in the right format. But we are missing a heck of a lot of information in the top. We need to rewrite that as x to the 7th, excuse me, plus 0x to the 6th, plus 0x to the 5th, plus 0x to the 4th, plus 0x to the 3rd, plus 0x to the 2nd, plus 0x minus 128. Look at all those terms missing. Some students would think that that synthetic division is going to be done in like 2 steps because they just think it's a 1 and a minus 1. This is what they think. It's all 1 minus 128. There's a 2 in the half box. Bring down the 1. 1 times 2 is 2. Add and you get negative 126. And this is terrible. Not even remotely close. Oh, I'm not hitting my undo button anymore. There we go. Okay. So for our synthetic division, since that's a minus 2, we put a positive 2 in the half box. To the right of that go our coefficients, which are 1, a whole boatload of zeros, and a minus 128. Make sure you get the right number of zeros. That's 1, 2, 3, 4, 5, 6 of them. 1, 2, 3, 4. Maybe a little more space. 1, 2, 3, 4, 5, 6. Then our minus 128 at the end. Blank row with a plus sign. This is way more work than what some students would think it actually is. But the way more work is still way less work than if you had to do this with long division. This problem sucks using long division. All right, bring down the first number, bring down the 1. Multiply, add, multiply, add, multiply, add, multiply, add, multiply, add. 1 times 2 is 2. That goes here, right? No, does not go there. That's where we're adding things. It goes here. 0 plus 2 is 2. Multiply. 2 times 2 is 4. Goes here. 0 plus 4 is 4. Multiply. 4 times 2 is 8. 0 plus 8 is 8. Multiply. 8 times 2 is 16. Add, you get 16. Multiply, you get 32. Add, you get 32. We're just adding 0 each time. Makes it easy. Multiply, you get 64. Add, it's still 64. Multiply, you get 128. Add, oh, we're not adding 0, but negative 128 plus 128 is Yeah, coincidentally, 0. Still quick. From right to left, remainder, constant, coefficient of x, x squared, x cubed, x to the 4th, x to the 5th, and x to the 6th. Meaning that our answer is x to the 6th with a 1 in front of it that I'm not going to write, plus a 2x to the 5th, plus a 4x to the 4th, plus an 8x to the 3rd, plus a 16x to the 2nd, plus a 32x, plus a 64. It's an ugly looking 6, but it is a 64. And there's no remainder, so that's it. I don't want to write plus 0 over anything because then I'm just going to get rid of it. When your remainder is 0, there is no remainder. There's no fraction. It divides perfectly. It means that the top is factorable and one of the factors would cancel with the thing in the bottom. That is an extremely important idea that I'm going to say one more time. When the remainder is 0, that means that the top is factorable and that one of the factors will cancel with the bottom. Text, text, text. When the remainder is 0, there is no fraction in the answer, which means that the top was factorable and one factor cancels with the bottom. We saw that in example D. We also saw that in example A. Another issue I'd like to bring up is when I did that wrong at first, I thought the answer was going to be like x minus 126 or something like that. Or no, I'm sorry, 1 with a remainder of negative 126. I don't remember. I don't remember what it was. I don't want to re-show it, but look at the answer. It's got an x to the 6th, an x to the 5th, and x to the 4th. It's got way more exponents in there. How do I know that that first one that I did super quick and terribly was wrong? Because this has an x to the 7th in the top and an x in the bottom. If you only focus on that, you'd get an x to the 6th. That tells you what the largest degree you should see in the quotient is. So an x to the 7th over an x means you should have an x to the 6th somewhere. Look at C, x to the 4th over x, that means you'll have an x to the 3rd in there. Let's look at a previous problem. Here with A, x squared over x, that means you should have at highest an x in the answer. X cubed over x, so you have an x squared in the answer. So if I have an x to the 10th in the top, I know there's going to be an x to the 9th in the answer. Has to. How are we on time? Oh, wow, I went over. I am so sorry. At least I only went 3 minutes over, technically speaking. I am sorry for that. So we will get into that idea of the remainder theorem, the factor theorem next time, how we can actually use this synthetic division for a bigger purpose. So we did not finish 3.3, but we did finish 3.2. So please start working on 3.1 and 3.2 as soon as possible, since chapter 2 homework's due tonight. But you still have another 24 hours and some change to get that test done. So again, thank you for hanging out the extra couple minutes. What time will this be up on YouTube? Within 45 to 60 minutes, because it takes a little longer process. It's a longer video. I usually have this done about 45 minutes usually. It has to sit and convert everything. So good luck with your tests. Please, please, please do not forget to take your test. If you don't take it, you're getting a 0. I don't want to give you zeros. I want to give you good A's, B's, and C's for good effort. 2 attempts. Best of luck to you. Have a good weekend. We'll see you on Tuesday on the internet. Take care.